Hello, in this video we're going to use R to confirm the theoretical calculations that we did in another video. This video that I just put out called Exponential Family Inverse Gamma, where we calculated the mean and the variance and the covariance of the sufficient statistics of an inverse gamma. And one thing that I like to do is always try to confirm the theoretical results based on simulations. And so this video will be using R to confirm the moments of the sufficient statistics of an inverse gamma distribution. Now, it should be noted that the gamma distribution that I like to use has the beta, or B in this case, in the denominator in both of these cases. It's also common to have it in the numerator, so this would be in the numerator. Here we're going to generate a sample size of 1 million, alpha 4, beta 2, y 1 million, because we can. The results would be much more accurate with the million, although if you used much less, it also still pretty good. So the one way to do an inverse gamma is to generate a gamma distribution with alpha and beta. Oh, notice this scale equals B. When you say scale equal B, that puts the beta or the B in the denominator. If you leave off scale and just put B, then it puts it in the numerator. It's also called the rate. And then to generate an inverse gamma is just 1 over that 1 over x. Now, in the video, the exponential family inverse gamma, we calculated the mean of the log of y. And here to simulate it, we just take the log of y, which is our data vector, and take the mean of it, and we get minus 1.94. Now in the video we calculated it as minus digamma of alpha minus log of beta, and that comes out to also negative 1.949. We calculated the mean of 1 over y, and we simulate that as 7.998, and then the theoretical calculations were alpha times beta, and here, which is 8, 2 times 4, and 7.99 is pretty close. The variance of the log of y, the simulated results are 0.28. The theoretical calculations is the trigamma of alpha, which is 0.28, the same. The variance of 1 over y, the simulated result is 16.0. The theoretical result for the variance of 1 over y is alpha times beta squared, which is 16. Now the covariance between our sufficient statistics, the log of y and 1 over y, the simulated results are negative 2 roughly, and the theoretical results are negative beta, which then is exactly minus 2. Now to be a little more fair, let's do this with the sample size of 100 and go through this a little more quickly. So here the simulated is minus 2, the theoretical is again negative 1.4. Then the simulated and the theoretical mean of 1 over y is 8.7 is simulated, 8 is the theoretical. So you can see that when you're dealing with a sample, so the simulated variance of the log of y is 0.3, the theoretical is 0.28, and so forth. The simulated variance of 1 over y is 17.1, theoretical is 16. So they're all in the ballpark. And of course with the million, they're the estimates and the true parameters are right on top of each other. The covariance minus 2.15 versus the theoretical of minus 2. Now I also want to investigate the correlation, and it is negatively correlated as minus beta. So let's look at the curves of log of x and 1 over x. So the log of x goes up like this, and then 1 over x is like this. And now, while they're not mirrored functions of each other, but they do, if you flip one versus the other, they look definitely highly correlated or negatively correlated. When one is big, the other's small, and vice versa. So let's calculate. Well, let's first simulate the correlation. So you just take the correlation of the log of y and 1 over y, and that simulated result, now remember this is based on a sample of 100, is negative 0.94, and the theoretical calculation, which is the covariance divided by the square root of the product of the variances, theoretical is negative 0.938, so also very close. If we look at a plot of 1 over y and the log of y, this is it. And so you can see that it is, it's negatively correlated and, sort of a line-ish. It's definitely not. That's why it's not a correlation of -1. But anyway, well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.